In this presentation, I'm going to teach you how to conduct a one-sided hypothesis test on the mean when our variance is known. So recall that in hypothesis testing, we basically can answer a question based on our data. So we may have an idea of what's going on, but we want to test certain ideas, and we use a sample of the data that we pull in order to answer those questions using a hypothesis test. In this case, for the one-sided hypothesis test, we're going to look at an example using fictional data on the lifespan of a Boeing 747. So let's say that Boeing reports that the average lifespan of the Boeing 747 is 25 years. And what we want to do is we want to test if the Boeing 747s that are owned by a company, let's say in this case US Airways, are on the order of what is reported, so that lifespan that is reported by Boeing. So with that in mind, what we can do is we can conduct a hypothesis test in order to determine whether or not the US Airways 747s are meeting that expected 25-year lifespan. So similar to what we did with the two-sided test, we have this process that we go through when we're actually conducting hypothesis testing. And just like the two-sided, for the one-sided version, it's 4 steps, and the first step is to define the null hypothesis and the alternative hypothesis. So in our case, we're going to define the null hypothesis that the mean lifespan is 25 years. So the mean lifespan of the 747 jet owned by US Airways is 25 years. Our alternative hypothesis states that the mean is actually less than 25 years. So I have collected a bunch of data, and from that data we're going to compute x bar, which is just our average of our sample. So let's go to Excel. So in Excel, you'll see that I've collected some data from US Airways, and I found that the average lifespan of 10 of their 747s are listed here. And according to our null hypothesis, our mu naught is 25 years. It also reports the population variance standard deviation reported by US Airways is 0.1, and our number of samples is 10. So the first thing we do after we identify or define the null hypothesis and the alternative hypothesis is we have to calculate x bar, which again is our sample mean. So in this case, we're going to type in average. We're going to select the years. And voila, we've calculated x bar. The next thing we need to do is we actually need to go in and we need to compute z naught. So z naught, again, is the same equation as we use in the two-sided test. It's that x bar minus mu naught is equal to sigma, or the standard deviation, divided or times the square root of the sample size n. And again, this z naught, this test statistic, allows us to sort of standardize our sample so that we can actually look at it using a standard probability density. So in Excel, in order to compute this, we just have to plug in our equation. So in our case, it's x bar minus mu naught divided by our standard deviation times the square root of our sample size. We hit return and we get a z naught of negative 2.84. So now that we've computed those, the next thing we need to do is we need to compute probability and then also the z of alpha. So you'll note here that I have it as alpha over 2, but actually, because it's not a two-sided test, it's only a one-sided test, we're actually just going to find z at alpha. And what we're going to do is we're going to compare this, when we find z alpha, we're going to compare that with our z naught at a certain alpha level, which is essentially just our confidence level that we're not going to have a type 1 error. Now before we go and actually solve for p, I want to sort of remind us what p actually is. So here's our standard probability plot. And it's standardized such that the mu is 0 and the standard deviation is equal to 1. And what we want to do is we essentially, according to our null hypothesis, we want to find the probability of z naught being less than some value of z. And so then basically our p-value, the probability that we're going to solve for, is the probability of observing a sample mean at least as extreme as x bar given h naught. So what we have to do in order to do that is that at a certain z naught, we need to calculate this probability. And for the null hypothesis to be correct, we're essentially saying that at this value, our probability is fairly high. So what we need to do in order to calculate that is we're going to plug it into Excel, and we're going to use the norm s dist function, and we're going to plug in that z naught value that we solve for. And essentially what this does is it actually helps us solve for the probability to the left of z naught, as I've already highlighted underneath the graph. So in Excel, again, we're going to type that norm s dist for z naught and hit return. And in this case, you can see that our probability is pretty low. And because it's so low, we can say that we're pretty darn confident that we can reject the null hypothesis, and which basically says that we are rejecting the hypothesis that the average lifespan reported by Boeing is higher than the lifespan of the Boeing 747s that U.S. Airways has had over the years. Another approach, in addition to probability, is to do the alpha value. And in our case, we're going to arbitrarily choose an alpha value of 0.05. And these are, 0.05 and 0.01, these alpha probability values are pretty typical in statistical testing. So let's look and see what this means. So basically we have an alpha value of 0.05, and using that we want to compute some sort of z alpha, and in order to do that, our z alpha is equal to the norm S inverse of 1 minus alpha. So basically what it's doing is it's going to use this probability for anything greater than 95%, and essentially use that to give us a z-score or z-value that we can then use to compare against our z-alpha value. So let's do that. So our z alpha value, again, we're going to use the norm S inverse function, and 1 minus alpha. And what we get is a z alpha value of 1.644. And in our case, our z naught is much lower than our z alpha value. And this just sort of further reinforces, in addition to what we've already seen with our probability, we can essentially reject the null hypothesis. So using both of these steps, both the probability and the z alpha, we've been able to determine that we do in case reject the null hypothesis. So basically we've realized that US Airways maybe isn't doing a good job of maintaining their Boeing 747s. But what we really need to do to see how meaningful this data is maybe to see how well they're maintaining their 747s compared to one of their competitors, so let's say Delta. So what we want to do is we want to sort of go back and go through that process again, but do a different hypothesis test to see how their average lifespan, how US Airways' average lifespan of their Boeing 747 is compared to Delta's average lifespan of their 747s. So again, we need to go back and define our null hypothesis. So in this case, our H naught is going to be mu naught is equal to 24, because 24 is the average lifespan of the Delta. It's the average lifespan of the Delta 747 fleet. And our alternative hypothesis in this case is going to be that mu naught is greater than 24. So essentially what we're trying to do is we're trying to see whether or not US Airways 747 fleet is the same as Delta's, or if it's greater than. So again, we're going to compute x naught, we're going to compute z naught, and then we're going to compute p and ultimately find z alpha. So let's go and do that in Excel. So we've already computed x bar because it's based off of the data that we have for 747 lifespans in the US Airway fleet. So z naught in this case is similar but slightly different because we have a different mu naught, and so our value is, again, it's x bar minus mu naught divided by standard deviation times the square root of our sample size. And we get a z naught of 0.316228, and then what we want to do now is we want to go in and solve for our probability and our z alpha so that we can determine whether or not we can reject or accept the null hypothesis. So before we do that though, let's kind of look at what we're trying to accomplish here when we solve for our probability. So last time we were looking at something down here, now we're actually looking for something up here. So we're looking for the probability at this value of z, which we'll show by being shaded underneath here. And essentially it's the probability where z is at least as extreme as z naught. So what we need to do is we need to think about probability slightly different, in that we want to find the probability such that it's 1 minus the probability that z is less than or equal to z naught. So in order to do that, we can actually go in and compute this in Excel. So again, we use that norm S distribution function. Before we go in and actually calculate that, I want to talk about the z alpha. And the z alpha here, again, is just some value of z where we know that the probability, which we're going to shade in here, is 0.5. And ultimately what we want is we want our z naught to be less than z alpha, because then we can, then we can't reject the null. So, in order to calculate the z alpha, we're going to use, again, the norm S inverse 1 minus alpha. So let's go do that in Excel. So first we're going to calculate the probability, and again, it's equal to 1 minus norm S dist of our z naught value. And we get a pretty high probability. So we see that probability is actually pretty high. And when we go in and calculate z alpha, our z alpha is equal to the norm S inverse of 1 minus alpha, and that's 1.644, and this value is in fact greater than our z naught value. And so according to these two tests, what we can determine is that we can't reject the null hypothesis, and as a result, we can say with fairly accurate, or with good accuracy, that the average lifespan of a US Airway 747 is equal to the average lifespan of a Delta 747. So as an engineer, that actually is really useful information, because maybe Boeing is inflating their numbers. So with that, I hope you have a better idea on how to conduct a one-sided hypothesis test when we know the variance using the mean.